53 total. Last week was about 60. I don't know if people are just dropping off or. Okay. So, okay, we'll get started. It's already 5 minutes. Yeah,
A
enough of
special
spamming.
class.
Yeah, enough of spamming now. Okay, let's start. Okay, so I'm hoping all of you were able to finish at least the first 2 questions or maybe the first 3 questions of the homework. Did all of you submit the homework? Is there anyone else who hasn't submitted yet? Okay, cool.
For me, what happening is I'm trying to submit it, but it's not going through. So try again.
Okay, so if you are not able to submit this, we don't know what's happening. So can you take a screenshot, like someone who is not able to submit, please take a screenshot and email that to us, because we don't know what's the error. And I think 2 or 3 people mentioned, but we don't know what is the problem. So let me share this email ID, but don't do this each time, because then it will be very difficult for us to coordinate. Maybe if you can connect to the website, message in the message center like a link to your PDF. If you have your PDF uploaded to like Google Drive or something, just message that link to your PDF. If you are able to log in and get to message at least. If you can't do that also, then email to this email ID. I'll just copy paste the email ID so that I don't type. So if you're able to message, upload your PDF to Google Drive, message the path to the PDF. If you're not even able to do message, just email to this email ID. Okay, yeah, so yeah, if you're able to submit, great. Yeah, yeah, some of you it's working. We don't know why it's not working for others. Maybe for those of you it's not working, it may be because you didn't register for this session. Each time you're supposed to register, because that's how the Agora Math Circle thing works. Right? Every semester, every 6 months once, or every session, we are asking you to register again, even if you are already registered.
Every
Maybe
semester.
right. Maybe that is a reason why it's not working. I don't know, but that's probably one reason. Okay, cool. So no, I think even if you don't register, you probably get the meeting ID. I think that's probably the problem. That's how you guys don't get the feeling that you haven't registered. I think because you can see the meeting ID even if you don't register. Okay, anyways, continuing on. So I don't want to like discuss each of the homework problems. Let's just go over the ones that you guys thought were difficult, and we'll just go over those. Let me start sharing my screen and disable annotations. Okay, so first question, does anyone want to like go over this the solution of this, or no, what is this? For 1B you wanted actors only, right? Yeah, I guess, yeah, 1B actors only. And like, what is the number of movies in which they acted, so that you know who is the most who is the actor who acted in the most number of top 100 highest grossing movies. Yeah, what was the answer? I don't know what is the answer. Yeah, you'll get the homework key later, but it's document, right? You'll have to understand from that. Versus, can I go over the solution? I don't know how many people have submitted, so that's why I don't want to go over the detailed solution, but I'll tell you the steps roughly if you guys had not done have had some difficulty. So I'm hoping the first part, at least nobody is having any issues. So this first part, everybody, I'm hoping we are able to do, like get the top 5 most popular movies by vote average in a given year. All that involves is change this to like vote average and remove this page, and just pick the top 5. Instead of this for loop, you could just say like some I less than 5 or whatever else you want to use. You could loop through this array and or loop through this list and get just the top 5 of them. That's what I'm hoping easy, right? Matthew, what's the question?
Nothing.
Okay. Okay, cool. So that's the first one. That's hopefully straightforward. The second one is a little bit more work. You start off with similar kind of thing. I'll already gave almost entirely the code, except that you start with page number 1 here. So you would exactly submit this request with page number 1. If you want to like write a for loop just to go from 1 to 5, do it that way. If you want to do some other way, that's up to you. You guys can do whatever you want. Just make sure you change this page number and query 5 times. So you'll get 1, 2, 3, 4, 5. Each page has 20 results. So you'll get in 5 pages, you'll get 100 movies. Right. So, okay, guys, if you want to talk about something that's not related, we'll just disable the chat basically. Right? You don't have to keep on spamming constantly, especially some people that I'm seeing constantly. Okay, if you have some question, message, because it's constantly distracting me as well. I have to keep looking at 2 things constantly, so distracting me will just waste time. Okay, so you can take this, use page number 1, 2, 3. All you'll get from that result is movie IDs. And then you use this second API, pass the movie ID. That gives you the cast and crew. Actually, this one I think I just done. So you can do whatever method you want to loop through pages multiple times. So I was doing something very straightforward. I was using like till the number of movies is less than 100 because I didn't want to assume that there are 20 per page. And I looped through this to get page number. Each time I get some results, I'm just incrementing the page number and moving on to the next query. Then I didn't want to assume everybody would be like a actor. So I just got all the cast and crew from a given movie and then looked for only actors. Then I created a dictionary where one of my key is the name of the actor and value is the number of movies they acted in, and then sorted that, and this is what I got. I don't know if this is the same thing that you got. So the actor who acted in the most number of top 100 movies is Jimmy Star. Yeah, and then Samuel Jackson because of Avengers and some old Star Wars. Scarlett Johansson, all Avengers probably. Then we see Robert Downey Jr. down the line here, right? If we restricted this to top 10 movies, maybe still Robert Downey Jr. might move up because I think he has more of those, but that's just it. So hopefully this is Emma Watson shows up. Yeah, lots of Harry Potters. So yeah.
I think Alan Rickman was the guy who played Snape. Am I right?
Oh, where is he? Yeah, probably. Yeah, I don't know. Let's Google. Okay, copy. Yeah, Alan Rickman is the guy who played Snape. Okay, so that's this final solution. Then fun with maps. Were you able to explore this API further?
One of the APIs you gave us didn't work. It was blocked. And then of the 2 APIs that did work, one of them already sorted it from closest to farthest from the longitude and latitude that you put in. So you didn't have to do one of the APIs.
Yeah, finding the nearest one, the one for finding the distance, that API was blocked, so I couldn't do.
Okay, yeah. You don't have to. Yeah, I think There are others. I actually didn't really specifically provide anything. I think in this one, just this API Explorer, whatever works basically. I tried a few and whatever worked for me, I basically tried out some form of solution, not really the exact one. That's why I don't have a solution for what the exact one is, but I was trying with a few static values and they were working. So yeah, some of these are probably blocked. Whichever is working here, you can pick that one. I don't know which one was the one that I tried actually, to be honest. But if you guys were able to make it work, great. This is the exercise here is no different from the exercise here. If you can do one, the other one is just a different application, just so you guys see different kind of things. Mostly about number of steps, really. How do you use different data structures to carry data from one result to the other result and keep going forward? That's all the overall exercise is. Just to get you like fair, because you used all these dictionaries, lists and all maybe 6-7 classes ago. So this is just like a refresher on that. Okay. Anyone, any questions on this one? Which is the better international roaming plan? Any questions on this one? Like, did anyone find it difficult or how to do, what to do? Okay, what's the answer? When does the flexible for one plan become more expensive than the unlimited plan? At what amount of data does that become more expensive?
5 gigabytes.
5 gigabytes, right? 5 gigabytes equal, yeah, right. So greater than 5 gigabytes, yeah, right. So you obviously don't have to solve this, right, to know this, because you could do this in your head. Probably most of you know how to do this without actually solving. But of course, the reason to say is this is the whole purpose of all of the exercises going forward. It's like we're trying to solve different types of equations, and the solutions to those equations are what are the decisions. Basically, this is a decision, right? In real life, nobody sits and solves equation for the purpose of solving. For 1B, you wanted to give us to give actor name, actor, number of movies, and what movies that. I don't remember name of movies. Maybe actor and number of movies was enough. Yeah, actor name and number of movies was enough. But I think the output I was asking for is like with these two as the keys. If you did actor name as the key and number of movies as the value, that's also okay. But if you did this better, you got 500 GB, thought it looked funny. Yeah, probably you did divided or did something wrong. Right, at 500 GB, what's the cost of the fixed plan? Actually, there is a cap really on this, even the flexible for one plan. I think I mentioned it somewhere below. No, not really. Okay. Yeah, so there is a cost limit on this one also. Like if you go to project fee or fi, however you pronounce, there is a $80 limit. So both plans end up being almost the same. If you use like more than 6 GB, just $10 more. Anyway, so this is what we are doing, is like trying to make decisions. So let's see if we can actually do this, because this will so what's the cost of flexible function? I'll do it in this cheat sheet I was doing. So what's the cost of flexible plan one based on the amount of data? How do you calculate? Used if else statements. Okay, that's good. But so what is the if else statement? Ten times amount of data plus 20, right? Absolutely. So I'll just return 10 times amount of data plus 20, right? That's it. Okay. What's the cost of unlimited plan? Just 70. So I'll just return 70. Okay. Now, are you assuming this data? I don't know, depending on how you guys program, like for you, was this amount of data a single number or was it a array? How did you guys call it? Okay, you guys called it with an array. Okay. So if you want to call it with an array, what do you do here? So the another way is 70 plus 0 times amount of data. You could do it that way. Right? That would work, because it doesn't matter. So the coefficient for this is 0, right? So this would also work. So you could just do 0 times amount of data plus 70 just to keep them in the same order. So this is the entire function. Just that the function looks simple, don't let it deceive you, because it's doing a lot of things. When you use some of these NumPy arrays, they are doing a lot of things in just short length of code. So import NumPy as NP is a common invocation. Okay, so now what do you do? How do you calculate? How do you plot this cost? So what do you do first? No, Agora website is not down. It's just taking too much time. We don't know why. I also couldn't get in on my first try. Like I had to try 2-3 times for it to work. Okay, so don't we need to use an if-else function in first? So Shruti, what is the if-else function? If data less than 1. Oh, good. Okay. So yeah, that's actually a good point. So if you, it's actually a very good point. So if data less than 1, right? Actually, this is not the simplest form of the equation, right? Like, so after I gave this question, I realized I didn't really like specify the exact one. It's just 10 GB for data. What if it's less than 1? Is it 0 GB, right? Right, so somebody said return data divided by 10 times 20. Why 20? If data less than or equal to 10, it's 10 per GB, right? It's $10 per GB. So you don't have to do data. This is fine. I think trying to do data divided by 10 times, I don't know why times 20. Because it's $20 per month for the line and $10 per GB of data, right? So there is that ambiguity. What if you use less than 1 GB? Yes, if you guys did it that way, great. If you use less than 1 GB, you only get $20, great. But actually, if you Google this one, project fee, they tell you that they'll charge you even if you just use 0.1 GB. They'll charge you $1 if you use 0.1 GB. But that's not the point. If you have done it that way, if there is ambiguity, I think I spoke to somebody or messaged somebody who also raised the same point. But the way the real plan works, they charge you like for every 10 for every 0.1 GB, they charge $1 really. So same as what we did last time, you divide this and then you do import math and math.seal, right? If you use 0.11, they charge you for 2.2 GB, right? So this is what you're really supposed to do, like $1 for every 0.1 GB, but it's okay if you haven't done it this way. For 15 GB, I thought $40. So flat $20 for 10 GB of data. No, not really. I think it's just for the month. 20 per month for the line and 10 per GB for data. Right? That's okay. It's all right if you use different ways of calculating. Yeah, the 10 per GB is 10 per GB, right? Yeah, that's okay. Even this collab link, yeah, I can send you this collab link. Right, so can take this one and then try this. It's okay if you have tried any other method. Let's just stick to the simplest one because I want to like go over the remaining part of this. There's no loss if you have tried with some other methods. If less than 1, if data less than 1, if the division method, whatever. Idea is more important. Don't worry about the actual one. As long as you got 5 GB as the answer, that's good enough, right? Okay, so now how do you generate amount of data? What do you do to generate? No, you don't have to use, as I said, like the actual implementation of this, the actual way this thing works. Because if you Google, this is actually a real plan from Google, right? So I went to Google's website, got this plan, and actually I was evaluating this a few years ago when I was about to go to India for a month and a half, and I wanted to go. I wanted to check if my international roaming on AT&T was better or this is better. Like I could just get one of these. And this is exactly the plan, $20 per month plus $10 per GB for data. Oh, they have a better plan now. It's $35 for 1 month for 3 months. Oh, I didn't know it was. So now this looks even more cheaper. Creates two lists in which money that needs to be paid will be stored. Cost 2. Okay, so somebody says np dot random of random 50 times 50. Why times 50, Shrish? Well, why times 50? Oh, it was 50 GB max. Okay, I don't remember, but okay. That's fine. So you could put some assumptions like that. There is no problem. So let's say, so we want to generate some random numbers to say amount of data. So np dot random of random. You can generate 50 values, 100 values, whatever, and let them be between 0 to 50, because you will not use negative amounts of data, right? And what do you do now? We want to calculate cost of flexible for one plan equal to this, right? And then the same thing, cost of unlimited plan is this. Let's just see if we can print this. Okay, referenced before assignment. So let's just call it cost of flexible for one, cost of unlimited. Okay. Oh, sorry, it's doing something here. We'll just say amount of data times 10. Okay, so it brought us some function results. Okay. Let's just call this one first and then try. What is it returning? Okay, so this is giving us some return values. Let's maybe try to return a list. That way it's easier, because right now it's returning some array, some function. Let's see if we can loop for cost in cost of flexible plan. See if we can loop through this. I don't know if it is. No, it's not iterable, so not a very good one. Let's loop through for data in amount of data, cost of plan, sort of when 10 times data plus 20. Okay, so now let's try this. Okay, so I added 20 to this instead of 70. So now we got some numbers. We have to now, sorry. Right. There was nothing wrong. I just wanted to loop through them and see the values. Right. Okay, so now import matplotlib as plt. Okay, and we want to say plt dot plot of amount of data, comma this. Then we'll also print the same one. So now we get some linear looking equation, right? So now you can see that these are intersecting at some point, right? So before that point, this blue line is cheaper. Obviously, the blue line is the cost of flexible for one plan. There are ways to label these things. And then the orangish line is the fixed cost one. That's the cost of unlimited plan. So this is the real purpose of like doing equations in real life, to make decisions basically, right? Anything below this point, so it would actually, it will be visually more better if you just did this for like 10 GB, no more than 10. So now you can see that, okay, right at the middle line, like around 5 GB, this is this plan is cheaper. Anything beyond this plan is more expensive. So does this make sense? Oh, yeah. Okay. So hopefully you were able to do this, and this is a simple decision making problem, which we want to continue further going forward. You still need access. Let me change share to something. Okay. Okay. Now let's try again. Okay. So this is one way of doing this. You could do it in multiple ways, like the internal code doesn't matter, but the result is really the plot. We want to see that the plot is working fine, right? Okay, so that's on that one. Did you guys, were all of you able to read this NumPy tutorial? Any interesting? Did you guys try out any other tutorial? Did you guys find any other better tutorials than this one?
Oh yeah, I used like 2 other sources, but I don't remember the name.
Oh, okay, okay. Okay, so hopefully you guys are all comfortable with basic NumPy stuff. And now, did anyone attempt this bonus question? Okay, okay, nice. So what's the, do you guys want to maybe share your collab session? We can see what's the output plot, because I don't want to sit and type this one more time. Who wants to share? Okay, Hari.
Let me share mine collab.
Okay. So what is this? How come it's interesting? Number of months plus amount of data. Okay. Interesting. So number of months, amount of data, number of calls. Yeah. So your function should now accept these three as inputs, right? Like it should accept number of months, amount of data, and number of minutes called as 3 input arguments, and then return the results for that. And the plot is also similar, right? Like you're not just plotting 2 things, you're plotting 3 things. Anyone else? Okay, so wait, ignore that. Okay, someone else shared. Okay, Jonathan.
Mine is at the bottom. I shared it again.
Oh, okay, yeah, 1 second. Let me go. So India roaming plan. Okay. Don't see what I was looking for. Okay, let's try someone else. So Jonathan, what you plotted is just 2 data points. That's the problem. I think like your random thing, you just picked 1 data point, right? You're supposed to calculate the costs over a lot of different data points. Then instead of getting just 2 dots like this, you'll end up getting multiple dots, and then you'll have a line and you'll get 2 lines for each plan. Okay, so next one, Shrish Goel. Shrish, access. Okay, Aditya Rohatgi. I don't know if, oh, same problem, access. This is with access.
I changed mine so you can view it now.
Oh, yeah, yeah. Okay, cool. So this is, I think, Shrish. Okay,
The
interesting.
bottom.
What's okay? Okay, so what is this one? Okay, you have cost of data, calls, and trip duration. Nice. So, oh, 70 times trip duration. Okay, so your trip duration is a number between 1 to 5. Okay, cool. Yeah, I think the small problem here, Shrish, is basically if you travel for 1 day also, it's the charge is 70, right? So here maybe you are better off picking integers, random integers rather than random numbers. So you would want to pick like random integers between 0 to 50. Sorry, 0 to 5, because I was going, so 1 to 5, I mean like random integers between 1 to 5. That would have been slightly better, because right now it's giving, it looks kind of not correct, because it's not just 70 times trip duration, right? It's like 70 for 1 month or less, 140 for 2 months or less, and so on. Right, between 1 to 2 months, anything is 140. So that's the only thing that maybe if you would have factored, your plot would have looked slightly better. But so is this plot appropriate? What is this plotting right now? It looks just like noisy, right? What you're plotting right now is just the costs. Can you tell from this plot when is something becoming expensive versus cheaper? It's plotting, yeah, total cost, right? Yeah, you're plotting just costs. But can you tell when is something, or what is the point at which, like when we did this linear one, we could tell, okay, this is a decision point. Okay, below this, buy this plan, above this, buy this plan, right? How do we do the same thing for this one? First of all, uh, for those of you who haven't done this, just bear with me. We'll continue with this as the exercise for today's class. So let's take this question. This is actually a real life situation, right? Like you don't know, I will use different amounts of data. I might make some number of international calls, and I'll probably, my trip is between 1 to 5 months. So with these number of unknowns, how many number of unknowns are there in this setup that we, oh, let's see Aditya's also, just to see. Okay, so should I just run this one? Okay. Right, right. So yeah, say, it looks like full amount of international calls, example amount, where plan 1 is better, plan 2 is better. Yeah. Yeah, again, I think, okay, so let's see. I think this is a good point for our start of this class. So first of all, for those of you who haven't tried this is a real life situation, right? How many variables are there in this particular situation that we are talking about? 3. Okay. Okay, anybody else who thinks there are 3 variables? Are there 3 variables? Okay, I'll rephrase the question. Are there 4 variables? Okay, what are the 4 variables? Oh, okay. Yeah, cost. Yeah, good. Yeah, cost is a okay. We can say how many independent variables are there? Cost is depending on those 3, right? Like, okay, so that's a good point. Yeah, 4 variables, 3 independent variables. Okay. Okay, so now let's see, if you had to write an equation, what will your equation for cost be? Let's see, I'll do this in Paint. Okay, so let's write down some equations for cost. Okay, what's the cost of project fee, or like flexible for one plan? What's the cost of that? Hopefully you can see. So how do I write the equation for the cost? Cost of flexible plan. Cost per month times math.ceil number of months plus 10 times amount of data plus time for all international calls in total divided by 100. Okay, very nice. Right. Okay. So actually, is that true? It's little more complex, but yeah, for the purposes of this class, we'll just assume this one. The problem is this, however, right? Calling to certain countries is charged at 1 cent per minute. Right? So that's purposefully vague, but okay, we can assume that equation. Why are we dividing by 100? Just because he's assuming time for all international calls is in minutes, and 1 minute's cost is 1 cent, right? Like instead of $1, it's 1 cent. So you could either multiply that with 0.01 or divide by 100, right? So that's the first equation. So we'll say flexible plans cost. You know what? Yeah, exactly. Yeah, that's what. Yeah. So I realize that's why. I'm just telling you how hard it is in real life to figure out these things. I'm not saying that the equation is wrong. I'm just saying in real life, when you do these things, these are super difficult because of these kinds of howevers, ifs. Okay, so let's take that equation. So this is flexible plan. Hopefully I can write faster. So the flexible plan's cost is, let's take Aditya's equation. We'll say cost per month. So that's 20 times, or I'll not write this times sign, 20 times ceil of number of months. If you used number of months as an integer, you wouldn't need this. If you were rounding off your number of months automatically, you wouldn't need this. But if you are generating random number of months between 1 to 5, then you need this number of months. And then plus 10 times whatever amount of data. So I'll say amount of data. And then I'll write it in the coefficient form, which is what we are following, and say as 0.01 times number of minutes. Our assumption is these are number of minutes of international calls. Okay, so this is for the flexible plan. Now, this is not where you would really use equations. Where we would use equations is when these things are known, right? So when the number of months are known, let me maybe circle this. In real life, if you are solving, you don't solve from this, right? This one is known. This is an equation that's known. You can just do number plugging and solve. But if all you know is these things, number of months, amount of data, number of minutes, and you have to figure out what are the associated costs, whether it is 20, 10, 0.001. If you have to figure out this, that's when you solve equations in real situations, right? Because this is not really an equation. This is just number plugging at this point, right? There is nothing to solve here. So, right, yeah. So what we have done here is just motivate like decision making, right? So first step was decision making. You can make decisions still by number plugging, right? At a different number, your one plan cost is higher versus another plan cost is higher. That is decision making. That's also important. But solving the equation, this is not about solving the equation really. This is just about making the decision, right? Now let's look at how to solve the equation, right? So if I did not know these 20, 10 and 001, so if I assume these to be X, Y and Z, which is what you guys probably did it in class, right? So if I assume this to be X, Y and Z, now what do I need to solve this thing? So now it looks like there are 6 things that are unknown. But assuming that I know these things, I know number of months and I know the cost. Right, so now what do you need? If I want to solve for this X, Y and Z, what are the things that I need to know? How do you set up an equation? So I don't know what is the cost per month. I don't know what's the cost per gigabyte of data, and I don't know what's the cost per amount number of minutes. But I know how many months, what amount of data, how many number of minutes I used, and what's the cost for each month, or what's my bill. I know that much. And I know this for a lot of people. So if I want to calculate X, Y, and Z, what do I do? Set up 3 examples and then find X, Y, and Z. Okay, let's try. So what are 3 examples? You guys pick 3 examples. It doesn't have to be one. Pick any 3 examples. So what do you guys want to be the number of months? What number of months do you want it to be? Okay, 2. Okay, so 2 times X. And then how much amount of data do you want? 47456. Okay, 1 second. We'll go step by step because for me writing in this paint is a slow process. 4,99. What is 4,99, Shayan? Oh, 4.99. Sorry, yeah, couldn't see it. Okay, so 4.99 months seems random, but because we want numbers to be an integer between 1 to 5. Amount of data should be an integer between 1 to 100. Okay, so amount of data, somebody picks 7. Okay, so 7y plus number of minutes of international calling, 51. Okay, we'll start with just integer numbers so that we don't end up getting crazy. So this cost is some A. Okay, we don't know the cost. We'll say this is just A. Okay, so second equation, you guys can just type the equation, whatever. I'll just write whatever first thing I see. Okay, 5x plus 10y plus 4 divided by z. Okay, we'll say 4z instead of 4 divided by z. Okay, 5x plus 10y plus 4z equal to b. Okay, and then 4x plus 5y plus 32z. Okay, equal to c. Okay, so now we have our system of equations. How many of you haven't seen this form of system of equations previously? If you have all seen, I'll not worry about talking a little bit more about this. If you have never seen this, we'll spend a little bit of time. Is there anyone who hasn't seen like a system of linear equations? No, these are now the variables, right? We have assumed some values for these months and we know some costs for that. This ABC, I just left it as ABC because I didn't want to put some number, but we could easily put 100, 200, 300, whatever. Right? We can change this ABC to be 100, 200, 300 just so that you guys don't stare at ABCs. Okay. So now we have three variables. Right. So now we have 3 variables, 3 equations. We should be able to solve. But has anyone not done this previously, please let me know so that I can talk a little bit about that. Okay, so looks like all of you guys know how to handle a system of equations. You have done 2. Okay, if you have done 2, then this is the same idea in general, right? Like, okay, so just for the sake of someone, so if you have done do something like this, x plus 2y equal to 10, or let's take that previous example. So 20 plus 20 is 40, and then x plus 5y equal to 70. So if you have a system of equations like this, just the simpler one, how do you solve this? Don't tell me the answer, just tell me like how do you solve it. If someone wants to speak out, that's fine. Yeah, okay, Hari, you can speak and say, okay, how do you do elimination? Substitution, elimination, 2 popular answers. Yes. So who wants to talk about substitution? Okay, Aditya, how do you do or Shruti, Satya?
You could solve for x in the first one, so x is equal to 40
Okay.
minus 2y, and then
Okay.
substitute that value into the second equation.
Okay, so this one, and then we substitute here, we get 40 minus 2y plus 5y equal to 70, right? And then what does that give us? That gives us 3y equal to 30 and y equal to 10, right? Very poor handwriting. I should get a tablet maybe and write on that from next class. I'll try before next class to set it up. Okay, so this is straightforward. This is substitution, right? You can do elimination. Okay, Vidyut, how do you do elimination?
First, you have to multiply one of the equations by -1, so you
Okay,
could so you can eliminate
so
the
I'll
x,
multiply first equation with -1 minus x minus 2y equal to minus 40.
and then you just add both of the equations.
So add my -1 times that to this. So what do I get? I get 3y equal to 30, right? So same story, y equal to 10. So we are happy. When you had 2 equations, very straightforward, right? You could easily look at it and you could figure out in a second. Substitution, elimination, 2 popular methods, no doubt. We could do the same thing for 3 variables also. In fact, some of these techniques are so old, like this technique of solving with elimination is about 2200 years old, before they even knew what to call this. This is from ancient Chinese methods. So very old methods, right? Nothing fancy. So all you're trying to do is, when you have 2 unknowns, you're trying to eliminate 1 unknown so that you can solve for the remaining unknown. That's it. Very straightforward thing. Or you can take 2 unknowns and write 1 unknown in the form of other unknown and then substitute back to the second equation and do it. So how many equations do you need if you have 2 variables to solve them? 2. Okay. If I give you any 2 equations, can you solve an equation for 2 variables? If I give you any random 2 equations? Right, yeah. So if you want to get a unique solution, oh, no, I mean, what I mean is, like, if I give you this x plus y equal to 20 and 2x plus 2y equal to 40, can you solve this one? Interesting. What's the solution for x plus y equal to 20, 2x plus 2y equal to 40? All real numbers. No, all real numbers is not true, right? Like, otherwise x plus y equal to 20 is not true. It's not all real numbers. So you can't get a unique solution. That's the problem here. Can't get a unique solution. So let's actually, let me open another pane, because I want to keep that second side of equation. So why are we not able to solve when I give an equation like x plus y equal to 20 and 2x plus 2y equal to 40? Why are we not able to solve this equation? I'm giving the same equation 2 times, absolutely right. Yeah. So one way of thinking about it is geometrically. How do you think about each equation? You can think of an equation in 2 variables geometrically also. It's like giving me a line. So if I have x equal to 20, y equal to 0, y equal to 20, x equal to 0, it's a line like this, right? So it's an equation for a line like this, right? So if I give you the same equation 2 times, any point on this line is a solution, and hence we don't have a unique solution, right? So this is just the geometrical interpretation of a equation in 2 variables, right? That's why we plotted. When we were plotting in that in that previous exercise, we got straight lines, and this is all it is. Algebraic representation, geometric representation, no difference. What if I gave you these 2 lines, x plus 2y equal to 20, or x plus y equal to 20, and x plus y equal to 30? Can you solve for these? No solution. Why no solution? It is not possible. Okay, why is it not possible? 1 plus 2 equal to 3. Okay, yeah, absolutely. 1 plus 2. 1 plus 2 not equal to 4. Of course, okay. Okay. So this is, when we are talking about a solution, we are talking about something that satisfies both these equations together, right? So what happens when you try to plot x plus 2y equal to x plus y equal to 30? You get a line something like this, right? Very poor drawing, but you get a line something like that. Oh, actually, I absolutely forgot. Why am I wasting time typing all this? So that's x plus y equal to 20, and then this is 2x plus 2y equal to 40, right? It's the same equation according to it. Hence, we were not able to solve. Now, if I change this to x plus y equal to 40 or 30, as what we were looking at, these are 2 lines that are Desmos is better. Okay, yeah, just something that I had used in the past. Okay, so this is the reason why these two, because these 2 equations are never intersecting, or these 2 lines are not ever intersecting, these 2 equations don't have a solution, right? Simultaneously solving both is not possible. What if I change this to say x plus 2y equal to 30? Now they have a point of intersection and hence a solution, right? So to get from this simple elimination technique, right, you could all immediately answer what was happening with this elimination. To get from that simple elimination technique to solving equations and further identifying when an equation is solvable took a lot of time. People did not know when an equation was solvable. Like as you guys said, immediately the reaction was, okay, if I have 2 variables, I should be, and 2 equations, I should be able to solve. But it took some time for it to be formalized into like, when will you really have a equation and a solution? So how many of you know when does an equation have a real solution or a single solution? When I have an equation like this, ax plus by equal to c, and dx plus ey equal to f. Do you know when is this form of equation has a solution? When does this pair of system of linear equations have a solution? Never? No. There is, okay. So there is a trick. Basically, you take ratios of the coefficients. So you do a by d, b by e, and c by f. If all 3 of them are equal, then you have no solution at all, or You have infinitely many solutions. Sorry, you have infinitely many solutions if all three are equal. Okay. If you have A by D equal to B by E not equal to C by F, then you don't have a solution. Why does that work? Because of the same thing that we just saw, because each thing represents a line, right? This A and B are the, if you rewrite this in the slope intercept form of the line, you get something like y equal to minus C by B minus A by B x, right? You get these, and these slopes are kind of telling you what's happening. So if you take the FC by F, that's really just telling you what is the distance or what is the intercept in some form, right? So when this is not equal, this is saying these ratios are the same. This is the situation, 1 by 1 equal to 1 by 1 is not equal to 2 by 3. So this represents a set of parallel lines. So this doesn't have any solution at all. When you don't have these two as not equal, and this doesn't matter really, so at that time this doesn't matter, then you have a unique solution. Actually, does it not matter? Let's check. So x plus y equal to 20, x plus 2y equal to 20. So do you have a solution for this? A by D not equal to B by D not equal to, I don't think this third part is necessary. So if you take this equation, if you subtract, you get y equal to 0, x equal to 20, right? Even when these two are equal, you will still have a solution. So as long as this ratio is not the same and these two are some non-zero numbers, then it's possible to solve. It's still a unique solution, right? Yeah, you get x equal to 20, y equal to 0 in this situation, right? So all these tricks were, it took about 1200 years to get to this much understanding of two equations in two variables. This is about 1200, 1300 years of maths probably. They didn't obviously have this intuition because this only came in like 1600s, right? Like how many of you know, like, or not 1600s, maybe they had like the intuition of lines, but this Cartesian coordinates and planes and lines in this form, that was not really there. Hence, when you guys study, you study in all the opposite order. When you when people were inventing this, they didn't know all these tricks, so they just toiled a lot for a long time. But anyways, now for seeing a pair of two equations itself, this seemed like it is abstract enough, right? Like, I don't know if it was clear to you, but when I learned this first time in like 6th or 7th grade, it was all like, actually it was, we were taught with little bit Greek letters also, so it was really Greek and Latin. So I'm hoping it is not that messy for you guys, and if it's messy, just don't worry about it. Think of it in its geometric interpretation. If you get two equations, you're really getting equations for two lines. Those two lines can either just be one line hidden in the form of two equations, or two different lines that are parallel to each other, or two set of lines that can intersect. Those are the only three possibilities when you get two equations, right? Either they are parallel or they intersect, or it's just the same line given in the form of two equations. And in each situation, you either have a lot of solutions, or never a solution, or exactly one solution. Okay, that's the story from this. Now, how do you do this when you have three equations? Right, so let me copy that back now. Now I want to, so for two equations, what did we look at so far? I'll just summarize whatever we looked at so far. So there were two, all of you, or at least some of you seem to know, there are two popular methods of solving them. One is substitution. One is I'll just very poor hand. Actually, I could probably write this put a text box and write it more easily. So one method of solving this is substitution. Other method is elimination. And third method is graphing, right? Not really a method, but just a way in which you could actually do if you were forced to do. If you were asked to do it in an exam, you would do, right? You would graph it and then figure out a solution. And each method has its own advantage or disadvantage and popularity and applicability or whatever. I'm not going to worry about all those things. And then we also saw, when is it possible to solve this? It's not always possible to solve a pair of linear equations. So solvability, or like when do they have a solution? Number of solutions, or right. So this is what we studied for just a pair of linear equations in two variables. Same thing as before, use first equation to isolate first variable, second equation to isolate second variable. Very nice. Okay. So this is all for two equations. So let me save this. I'll probably just use this in the class note. Two. Okay, so oh, okay, fine. So now let's take this equation we wrote here. Okay, so now who wants to volunteer to solve this thing? It looks like I'm taking way too much time on this paint. So if you guys want to try on your own computers, notepads, in your head, whatever you want to do, whichever method, any method is fine. So substitution or elimination. So who wants to try substitution? You can try. Someone who wants to try elimination can try. Graphing this on 2 dimensions is not possible, but if you have the imagination to imagine a 3D plane and find its intersection points, that's great, but it looks incredibly complex to do in my head. Okay, okay, try, yeah, go ahead, please try, yeah. You guys can do it on your own computers, right? Try to solve this pair of equations using substitution or elimination. So for those of you who are trying elimination, yeah, 51Z, sorry, yeah, poor handwriting. 2x plus 7, I'll type here, I'll type the equation. No, not code, like, well, let's first do with math, pen and paper style. So I'll type the 3 equations here just so that you guys can try on your own. Yeah, you can try for like 2-3 minutes, see if you guys can solve. Yeah, somebody mentioned, yeah, using code. Yeah, we will solve this using code also today, but not yet. Our objective is to understand everything mathematically, algebraically, geometrically, and programmatically. So we'll try to do all 3 methods. Just that in this case, doing geometrically on pen and paper seems just too hard. Something weird is happening. I'm seeing all these comments you guys are typing on my phone, but I don't see that on my computer. Okay. Okay. Yeah, I'm not sure if that is. Oh, okay, finally I got some message here. Very weird. I don't know if it's correct, but let's see. Others can verify. If you want, I can also try solving. It looks like a very big coefficient, 10,103,000 divided by 1119. So which method did you try, Sriram? Okay. So Sriram, maybe Sriram can explain what method he tried, or whoever is the person messaging as Sriram. Elimination. Okay, let's try elimination. So what is the easiest target here? So basically look at this 2x, 4x. So that's the first target, right? 2x, 4x, you multiply this by 2, subtract from this, you get 1 gone, right? So if you multiply this equation by 2, you get 4x plus 14y plus 102z. And then you subtract this from that one, you get 0x. So right, so you get 0x plus 9y plus 70z, right? 9y plus 70z equal to 100. No, minus 100. Wait, you have to equal out the y's also. Yeah, you have to equal out the y's also. Then you take these two pairs, or maybe, yeah, take these two pairs and then multiply this. You get multiply this one by 5, multiply this one by 2. You get 10x plus 35y plus 255z equal to 500. 10x plus 20y plus 8z equal to 400, and subtract so 25y plus 247z equal to minus 200. So now I have eliminated x out of the equations. I got one set of y and z. I can again repeat this and do same thing. Just that what is the LCM of 9 and 25? 225. So let's multiply that with 25 here. This is 1750z. And this is 1600, 1960 and 63, 2063. So I get minus 2500 and minus 1800. So if I subtract, I get 63, 263z equal to 700. So z equal to 700 by 263. I don't know if I did it right or wrong, but if anyone else has done it, can you please check? How did I get 9y? So oh, sorry, I'm not looking at messages as I was doing. So what I did is I first multiplied this equation by 2, right? So what do I get if I multiply this by 2? I get 4x plus 14y plus 102z equal to 200, right? And then I subtract this equation from that one. So I get 14 minus 5, 9y, and 102 minus 30, 70z equal to 200 minus 300 minus 100. So that's what gave me this. Then I take these two and multiply this by 5 and this by 2. So if I multiply that by 5, I get 10x plus 35y plus 255z. Oh, I think I made a mistake. I don't know if I made a mistake, but let's see. So 10x plus 20y. Yeah, it looks like I made a mistake, right? Yeah. 10x plus 20y plus 8z equal to 400. So the second equation is 15y plus 247z equal to 300, not minus 200, it's plus 100. Right. How did I get two equations? I'm taking these two equations and multiplying them by something. Right? And then I'm subtracting those equations to get this set. What was the answer? Now I don't know because I made a mistake. So now it's 19 and 15. So 9 and 15. What is the LCM of 9 and 15? Easier LCMs. 3. Z is 800 by 391. Okay, let me check quickly. So this is multiply 5 times, so 45. So that's 350Z equal to minus 500. And multiply 3 times, that's 741Z equal to plus 300. So subtract gives me roughly 350. So 341. No, 390. No, 391Z equal to 800. Yeah, so Z equal to 800 by 391. Whoever got that first. Yeah. So Z equal to 800 by 391. So this gave us one answer. Now what do you do? So after you get Z equal to 800 by 391, what do you do? We substitute it back. Wonderful. So this looks like the lesser, slightly more friendly way of substituting back than this. So 70 times this. Oops. I'm not even going. Let's try if we can solve. I want to see how long it takes to solve this so that we can motivate the next method. So 70, 800 divided by 391. So y equal to minus 100 over 9 minus 70 times 800 by 391 times 9. Right. Okay, so somebody already figured it out. Okay, so 391 and it's not possible to have 800 by being charged for we have round. Yeah, absolutely. Yeah, this one is made up numbers. That's why we are getting made up equations, right? It's not possible that the cost is 100, 300 for exactly also, right? Like, so that's where it went wrong. So we made up the right hand side of the equation, hence all our coefficients are made up right now. So anyways, whoever solved for this, what did you get? Minus 31,700 divided by 1173. Okay. I'm believing that's the correct answer because I don't want to sit and type all this, but we can check shortly. Can you show how you solve two equation once again? You mean this one? This one? Meda, is this what? No, okay. Like how I went from this 9y plus this thing, how I went from this to get this solution? Right, yeah. So I took, again, same elimination. I noticed that if I multiply this 5 times and multiply this 3 times, I get 45y, 45y, right? So when I multiply this 5 times, I get 350z and 741z. So then I subtract these two, 741 minus 350 is 391. And because I multiplied this first one by 5, this is minus 500. The second one by 3, this is plus 300. So 300 minus of minus 500, 800. So I just continued the same elimination method. Let me undo. Hopefully it will paint the previous equations. Right. So I multiplied this one by 5 and this one by 3. I got 350z. I have to say like 45y plus 45y, but anyways, I was about to cancel, so I didn't write those things. So ideally you get this, right? So 45y plus 45y and this, right? Now I subtract this first equation from this second equation. So I subtract this to get 391 y z equal to 800. If any one of you doesn't follow this, please let me know, because you have to understand how this is happening to understand the next method. And understanding is important because we'll obviously do this through programming, right? We'll not do this like this. We'll do it through programming in future classes. But if you don't understand what's happening, and then you don't really know why it's happening. When some things go wrong, you don't understand why they are going wrong. So you have to understand at least the fundamental idea. So elimination works, right? So you eliminate and back substitute. So this method works, right? It's possible. And then somebody said y is equal to minus 31,700 by 1173 and x is something else. Did anyone solve for x already? Oh, you don't understand. Okay. Shreyan, can you say what is it that till where did you understand, Shreyan? Maybe yeah, you can speak out so that I understand till where did you understand? Oh, none of it. Okay, that's interesting. Did you understand this one when we tried the solution for two equations? Okay, so why don't you try first with this equation? This is a very simple equation. How can we eliminate x from this pair of equations? Shreyan, is there any way you can eliminate? We have two equations. How can we eliminate x from these two equations? You can add them together. You can subtract one from other. Okay, right. Yeah, you subtract one from other, and now you lose x, right? So you subtract any order. So your x minus x is 0, and then 2y minus y is y. 20 minus 20 is 0. So you got y equal to 0. That's elimination. The idea of elimination is I eliminate one variable out of the pair of equations, right? When we had three equations, I took the first and third equation, multiplied the first equation by 2, and subtracted the third equation from that. So I got 4x plus 14y plus 102z equal to 200. So I multiplied the first equation by 2 and then subtracted this. I ended up getting this one, 9y plus 70z, right? I did the same trick with again the first two equations. I initially used 1 and 3, then I used first 1 and 2. I multiplied first equation by 5, second equation by 2, and got some other set. I subtracted them to get this 15y plus 247z equal to 100. Those two equations are here. If you subtract these two equations, you end up getting 15y plus 247z equal to 100. Then I did the same trick. I multiplied this by 5 and this by 3. I got 45y plus 350z equal to minus 500, and this. Then again I subtracted them. I got 391z equal to 800. Finally, I found out z equal to 800 by 391. If it's still not clear, we can discuss at the end of the class, because I want to move forward. You could do all of that in a single step. Well, yeah, I mean, yeah, of course. You mean
That helps a
programmatically?
bit more.
Oh, okay, cool. Yeah. So Shrish Goyal, when you're saying you could do all of that in a single step, are you talking about like programmatically, or you know some trick in which you can just look at this set of equations and in one step write the answer? If you find the LCM of all the coefficients of x and y, okay, what is the LCM of all the coefficients of x and y here? 20, right? Right. And multiply the equations by that number. You mean to say like first one by 10, second one by 4, and third one by 5. Okay. Right. Then all x and y will cancel out, leaving z. No, they'll not cancel out. Try. Let's try. So what is the LCM of 2, 5, and 4? What is the LCM of 2, 5, and 4? 20. Right. So now multiply. Now what do you want to multiply with? No, the LCM of 275, 10, 4, 5. Okay, what's the LCM of 2, 7, 5, 10, and 4? Right, now let's see. Actually, no, I want to see. I'm interested. 140, right? Perfect. So 140. So you multiply the first equation by what? So you found the LCM, but what do you multiply the first equation by now? By 140. Okay. So you get 140 times that, you have 280x plus 980y. But you okay, what do you multiply all of them? Okay, so you multiply that, so multiply the first equation by 140, so that gives you 280x plus 980y, and then it gives you, in the second equation, if you multiply by 140 again, it gives you 700x plus 1400y. So nothing got eliminated. Yeah, there is no one-step solution to this one. The method of elimination is the most common trick used for solving linear equations, and that's a step-by-step process. There is no other single shot trick. There are, if you ask a program to do, you can write a single line code and solve it. In fact, actually, taking LCM of all of them together, what does it even represent? It doesn't represent anything, right? Why are you taking the LCM of coefficient of x and coefficient of y? Yeah, what do I do after I solve for z? After I solve for z, I will take this and put this into this equation. So 70z will be this times 70. And then 9y plus that is minus 100. No problem. Yeah. So once I put that into that equation, I get 9y plus 70 times 800. I'll not write this. I'll just say 56 times 10 cube, or 56k divided by 391 equal to minus 100. So now I have two numbers. So this is just 56,000. Okay, let's just write it anyways. Now I transpose whatever 56k is 56,000. Yeah. So transpose this or take this on the other side. You get minus 391,000 minus 56,000. So how much is that? 95,100. So minus 95,100 divided by 391 times 9. So whatever this simplifies to, I have no way of. But why are you doing 56,000? Or actually, you don't have to do 56,000. Just when you, what is 7 times 5? So I want to substitute the z here, right? If I want to substitute z, I have 70 times 800 divided by 391, right? So 70 times 800 divided by 391 equal to minus 100. So I substituted this back into that equation. Is this clear? Very nice. Yeah. So whoever that took 3519, absolutely. Right. So now you substitute here, you kind of solve this number, or you transfer that side and solve everything. You'll get some simpler, some fraction for y also, right? And whoever already solved, what was the solution for y? Minus 31700 by 1173. That was their solution. I don't know if this is correct. I'm just writing it because two different people wrote it. If someone wants to check, you can check. Actually, let's just do it and see if this is adding up. So 800 divided by 391 times 70 is just 143. This times -1, 143.22. Let's just make it minus 143.22 minus 100 divided by 9. This is minus 27 point something. So is 31700 divided by 1173 close to that? Yeah, so that seems right. Yeah, we'll have a break as soon as we solve. Vidyut, we are learning how to solve equations. If you are not learning that so far, then maybe I don't know what you have been listening to. But we are learning how to solve equations algebraically. Then we'll see how to solve this programmatically. Okay. So finally, you use the same. Once you get x and y, you put them back into some friendly equation like this, and then you will get x, right? So I don't know if anyone has solved for x, but if someone has solved for x, what is it that you got? Did you find a solution for x? 108,400 divided by this. Okay. Divided by 1173. Okay, perfect. So we got this. So whatever these answers represent, 92. Okay, cool, super. So something is close to 27 minus 27. Something is close to 92. And the first one is close to 2. So roughly, I'm just trying to make these integers, but we don't have to make them integers. Yeah, so this is one method of solving equations, right? Right. So good, perfect. So that's it. So this is a good point to stop for now. You can take a break for 10 minutes. Be back by 11:10. If anyone has any questions on how we have solved this, once we are back, we'll look at how to do this more formally and how to do this programmatically. Okay, cool. So you guys can take a 10-minute break. Oh, very nice. Good argument about what is 1 hour break versus what is leaving. Yeah. Whoever wants a 1 hour break, just don't show up this class, and after this. Is there an easier way to do this? Actually, yeah, probably that's what we are trying to solve, right? How do we get to 2 equations from 3? So Vidyut, let's try. I want you to try this one on your own so that you can figure out. Let's take somewhat more easier equations. Okay, so I'll have x plus y plus z equal to 4. Okay, and 2x plus 3y equal to 3y plus 4z equal to 8, right? Now, Vidyut, how can I get rid of x from these 2 pair of equations? I'm allowed to multiply one equation by a number, and I'm allowed to add or subtract equations to each other.
You would multiply the first equation by -2.
Okay, so I multiply this with -2, I get minus 2x, and then I would get minus 2y and minus 2z. Okay, so minus 2y minus 2z equal to minus 8. And then what do you do?
And then you add both of the equations to each other.
Perfect. If you add these 2 equations, what do you get? 2x
You
and
get
minus 2a?
you get y plus 2z is equal to 0.
Right. So now you got, when you took 2 equations in 3 variables and you eliminated one variable, you got one equation in 2 variables, right?
Yeah.
When you have 3 equations in 2 variables, you take first and second equation, eliminate one variable, first and third equation, eliminate the same variable, then you get 2 equations in 2 variables each.
Oh, okay. Thank you.
Yeah, no problem. Can you subtract two equations to get rid of one? I don't know. You can subtract, yeah, sure. Anyone else has any other questions? Shrish Goel, can you subtract two equations to get rid of one? I'm not sure what you mean by that. Like, Shrish, can you explain like what you mean by that? What do like sub the 2 and 3 and oh yeah, I guess you could, yeah, but you could take any pair of two equations, eliminate for one variable. Right, yeah. Unfortunately, there are no special tricks, right? Like there are some circumstances you could use some other special tricks, but in most cases, this is the painstaking manner in which you have to solve these, right? Like take a pair of two equations, eliminate one variable, take another pair of two equations, eliminate one variable. You have now reduced the system to a smaller set. Then you continue, you keep moving on. And you keep moving on till you get to like two equations or one equation in one variable, and then keep back substituting continuously going forward. Let me see if I can maybe. Okay, let me see if I can get into focus on this board more easily. Then it might be easier to. Oh, I have to get a bigger board for next time maybe. Can you guys see my whiteboard?
I
we
can't really
can-
see it
Yeah,
that
we can see like
well.
the corner of it, like the one that.
Yeah,
you're
I'm
using.
just trying to erase one corner to show what is happening, but
I'm able to see it.
okay, let's see if I write on this, is this clear? So that I can see if I experiment with this mode. How to experiment?
I can only see one side of your whiteboard.
Yeah.
Right,
actually,
yeah, I'm only sharing one side of my whiteboard also, but is this visible? Like, but no, you can't
It's-
see. Oh, okay, yeah, now you can
Well,
see.
Yeah, I
it's
mean,
visible.
I can see it. It's just like it's just that I have to pin your screen because
But
it's
Okay.
pin screen.
I think
Yeah.
what will help is you should stop sharing your screen so we can see it.
Right, let's see if I stop sharing my original screen. Does this work any better? Okay, so does this work?
Weird.
Oh, no, on my screen also I lost that. Is this visible, clear enough? IVX.
Yeah, I'm able to see it.
Yeah, okay. Let me see. Maybe by next time I'll try to start off on this board. It is much faster for me to write this way also. Okay, so yeah, once everybody comes back, let's see if this is clear to everyone, but I'll have to figure out how to place my camera in one position and have a board. Maybe tablet is still easier. Do your teachers use, like in school, any tablet, any software? Do you guys know anything? You guys know more than me about this stuff.
When
There's something called a Zoom whiteboard, and that is a whiteboard on Zoom.
Right, but that's the same still, right? I need either a stylus on or a tablet or something to do that.
Probably just
So
need to
what
get one of those
happens with
drawing
my,
tablets and then just connect it to your computer.
Right, yeah, that's what.
my 3D modeling teacher, what he does is he connects with two computers. One is a tablet and the other one is a desktop. And whenever he needs to my algebra teacher does the same thing. Whenever they want to show us something like by drawing or writing down an equation or something, they share their screen with the tablet, and then they open the Zoom whiteboard on their tablet and then draw over
Got
that.
it. Right, yeah, I'll also try something like that. Actually, I can probably
You
try.
can
I
see
have
if
a
you have a touch screen. If you have a touch screen, I think, and I like a
yeah, my laptop
size.
has touch screen, but problem is it's.
You can
Let
see
me
if you
see
have
if I
like a
share my
stylus.
screen from my phone. What happens? I'll stop sharing video. I have a stylus on my phone. Oh no, share screen. Okay.
Even if your computer has touchscreen, you can also do the same thing on your computer.
Yeah, but
That's what my algebra teacher does.
Can you guys see my screen right now? Like I can't
Yeah.
see what I'm.
Yeah, I
Okay.
can.
I can see your screen.
and you can
Okay,
do like
so
work
let me
using
see on
stylus.
this one. If this works, then I don't have to worry about anything else because I have a.
Yeah, we can see it.
Okay, so this is cool. Okay, so I should have figured out this one before. I would have saved a lot of time. Okay, 4x plus 5y plus 32z equal to 300. Okay, so this was our first pair of equations. We considered these two and these two pairs, and we eliminated to get. So the goal of elimination is to come from three equations to two equations. Let me see. I mean, from three variables to two variables, or whatever is the higher number of variables to one less, right? With one set of eliminations, you can get that one less variable or one variable completely eliminated. And then we do one more time to get, so we initially eliminated x, now we are eliminating y, and we end up just getting to do that, we have to do this. Hopefully everybody is back. I'm just going without checking, but you do something along these lines. And now eliminate z to get eliminate y to get this, right? So this is the process of elimination. So as you go from top to bottom, you are doing elimination. Then you do something called as back substitution. You take this, put it back here. You take that, put it back into one of these equations. So we do that. That's called back substitution or substitution, whatever you want to call. So this is one method of solving linear equations in two dimensions, or sorry, in more than any number of variables. It doesn't matter as long as you have a system of linear equations and sufficient number of linear equations. This is one method to solve. Yeah, phone charging is going down, right? Yeah. Okay, cool. So now let's continue. How many of you thought this method was simple? Is this method, does it sound simple? Yeah, it totally sounds simple. Absolutely simple. Well, yeah, you guys seem to be very smart kids, but most people wouldn't consider this something to be very simple, right? Method is simple, very, very simple. Yeah, yeah. Yeah, it's just that it took human beings as a species about 2000 years to figure out this method that sounds so simple today because we figured it out. or somebody figured it out 300-400 years ago. So the first mathematician to figure out this method is called Gauss, or Carl Friedrich Gauss, a German mathematician. You guys might have heard of him. And he came up with a slightly more simpler way of doing this without writing these equations. So see, I'm writing x every time, y every time, z every time, right? So he just dropped those. And this method of dropping has been there for quite some time, like dropping the variables. So he just wrote this like this. 254, 710, 5, 51, 432. And then he just wrote it this way. So it's just, according to him, these are just a bunch of numbers, like a grid of numbers. Seems simple, right? No, actually, he didn't get to matrices yet. That was another 150 years later, actually. So the problem, that's what, like when you're taught in school, you're taught opposite order in which discoveries are made, because it's easy to teach and say, this is the method, follow the rule, right? When Gauss did, he was trying to measure the influence of 6 variables on planetary movement. He was looking for he was looking at certain, I don't remember the name of the body, but he was looking at the motion of a particular, what he thought was a planet. It probably didn't turn out to be a planet because I don't remember the name, else we would have remembered the name. Or maybe it was christened as some other planet later on. But he was trying to find out the paths of planets and what variables influence the path of a planet. And he noticed that he had a system of 6 equations in 6 variables, and he was trying to solve that one. So he had 6 rows, 7 columns, right? So that's what he had. So you could do the same tricks again and again on these things, right? Like you could do 2 minus 2 times this first equation and add 2. So you can do minus 2 times first row plus third row. This method of solving this is called transformations. You can do minus 2 times row 1 plus row 3. This is called Cayley-Hamilton or some substitution. I forgot the name, but was invented by this guy called Arthur Cayley, a British mathematician in 1800s or something. So this notation, just I don't remember if it is even right, but I'm fairly certain that's the guy. So he invented this thing. And what Gauss did, because Gauss invented this method, this is called Gaussian elimination. Even though it sounds so simple, right? This was known to ancient Babylonians and Chinese guys, but you don't call it Chinese elimination or Babylonian elimination, you just call it Gaussian elimination, because in this modern form, he was the one who formalized this. In fact, in modern form, this is how this is written. You put a square bracket around this to just make sure that this is these numbers are all related, just so you don't, and then you put a line here to say something that this is the left hand side and this is the right hand side. So this is the modern form of writing Gaussian elimination. Of course, Gauss didn't write it in this style. So you do that whatever we discussed previously, and you continue and complete this. But it looks tedious, right? Even if it is simple, it just looks tedious. This method is tedious, and this doesn't tell much about, hey, when is something solvable? If you remember, when we had 2 equations, when you had this ax plus by equal to c and dx plus ey equal to f, we could write a nice simple equation to say if a by d equal to not equal to b by e, we'll get a single solution irrespective of whether c by f is coming into play. And if you get a by d equal to b by e not equal to c by f, you get no solutions, and a by d equal to b by e equal to c by f, you get infinitely many solutions. So you got a nice system right here. It was very straightforward. So people started thinking about, how do I know when does an equation have a solution, right? So there was no easy way to answer that question with this kind of a simple format. At least there was no easy, if I write this as ax plus by plus cz equal to d and so on, it just becomes extremely messy. So what they realized is they could try to figure out when does this elimination not work, right? Because they were trying to do Gaussian elimination for solving equations. They figured out when does this elimination not work, or when does it not give an a solution. So to do that, what they did is they separated out something like this. They took our seemingly friendly equation, said okay, 2, 5, 4, 7, 10, 5. Would have been easier if I would have written numbers that are easy to write. They took this and then they said, okay, hey, you know what? An equation is really just something called a matrix, right? You guys are familiar with this as a two-dimensional list from Python, right? This is now a matrix for us in mathematics. And you multiply that with a vector with x, y, and z. And you get another vector, 100, 200, 300. So they first came up with this notation. This is all just notation, right? Nothing fancy, still just notation. Using this notation, you could do some analysis. And that whole analysis is called linear algebra. Currently in modern style, you call this linear algebra. And that's where it all starts. But is this clear to you guys how we took this pair of equations here? 2x plus 7y plus whatever. Let me see if I can copy this. And how do I paste this? Right. So we took this equation 2x plus 5y plus whatever. And we are rewriting it in this form. That's all. There is no difference really. Both of these I'm claiming are the same, just a different way of writing. I just took the 2, put it here, took the 5, put it here, took the 4, put it here, 7, 10, 5, and so on, right? But now if you notice that I did something weird with this x, y, and z. I didn't write x, y, and z in the column format. I didn't say, hey, I'll take the x here, put it here, I'll take the y here, put it there. I didn't do that. I noticed that x, 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 and y, y, y are the same on this. So I just converted that into some single line. And this is a big leap, right? So this writing this like this is just because it's the same x, whether I write x, x, x like this. Ideally, I was supposed to break this into two things. If I was supposed to break this into two pieces, I should have done 2, 5, 4, 7, 10, 5, 51, 4, 32, and I should have done x, 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 y, 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 z, 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 right? It took me so long to realize the numbers and variables were based off of the 3 linear equations from earlier. Oh, okay, cool. Right. So this, if I should have written it like this if I'm following my own style. But if you notice, this is just repetition, right? X is repeated 3 times, y is repeated 3 times. So they just thought, okay, why not invent something fancy and then just take one x from here, one y from here, and one z from here, and just write it as a vector. So if you have a single column, it's a vector, or sorry, single column, multiple lines, it's called a vector, right? Just some notation. So this is also a vector. How many rows are there in this matrix? How many rows are there in this matrix? 3. How many columns are there? 3. So this is a 3 by 3 matrix. Just these are some just notation, right? You don't have to. Can you review? I'm kind of confused on this notation. Okay. So you are familiar. These were our 3 equations, right? So these 3 equations, what we did is we took each of the coefficients of x and wrote them without writing the x. So I wrote 2, 5, and 4. So I wrote, this was a 2, I wrote 2 here. There is a 5, I wrote 5 here. There is a 4, I wrote 4 here, right? I dropped the x's because they are common, right? X is the same thing, irrespective of whether I write. And then I took the 7 and 7, 10 and 10, and 5 and 5. And I wrote them in the second column. And then I took the 51, 4, and 32 and wrote them in the third column. Is that clear, Prince? What's a vector? Just a name. Okay. Yeah. But why x, y, and z on the other side? Yeah, that's a good question. So which variable were the coefficients 2, 5, and 4 for? What was this variable corresponding to? What was this variable corresponding to? 2, 5, and 4 are the coefficients of which variable? X. So I wrote x. The whatever I wrote in the first column here, I wrote as the first row here. Whatever I wrote in the second column here, I wrote in the second row here. Third column here goes into the third row here. This is just a notation. This notation allows for some friendly operations later on. And the reason why this notation was even interesting is because when you do elimination, all you care about is the coefficients, right? You don't care about the variable. When you do elimination, as long as you keep the columns correct, you don't need to know this is for x, this is for y, this is for z. As long as all of these are for x, all of these are for y, and all of the third column is for z, you don't have to worry about it. It's I have a small cursor also that shows up. Okay, yeah. Oh, cool. I'll have to figure out how to make that cursor a little big. So once you do it in this format, this is a 3 by 3 matrix. This thing over here is a 3 by 3 matrix. This is a 3 rows by 1 column matrix, right? So this x, y, and z has 3 rows and just 1 column. So 3 by 1 matrix. When you have 1 column, it's called a vector. That's all. So what's a vector? Nothing. It's just a name for one columned matrix. But it has other interpretations in other branches of mathematics and physics, and we can talk about that little later. Okay, so far clear? So I took an equation, I converted it into its matrix form, right? I took a system of equations and converted it into the matrix form, which is like this. Now I'll give it abstract names. I'll say this matrix is A and this vector is X, and this right hand side vector is B. Why is none of this stuff on the lecture notes? There is no lecture notes, right? Where is lecture notes? Oh, you're talking about that collab thing? Last Friday? I don't know what was posted last Friday. That's probably from the previous class. Yeah, there is no lecture notes for this class. After the class, we are posting class notes. We are not posting lecture notes ahead of time. Yeah. Okay. So this is a notation, and this is
Wait, so you post the
matrix.
class? Oh, sorry.
Yeah, we're just posting class notes after the class.
Okay.
Homework from state. Yeah. Yeah, so I think I mentioned last class, right? Like if you whatever date we are posting the homework, you have 8 days from then. But somebody brought up this one, and we'll discuss. Maybe we'll just give you like till the Friday before that. Whenever we post the homework, till you'll have like 10 days or 8 days or 9 days or whatever, but you'll at least have 8 days. Okay, so this is a notation Ax equal to B. How many of you are familiar with this? How to solve this equation 2x equal to 3? Okay, perfect. So is there anyone who doesn't know? Yeah, divide by 2, right? So you simply do x equal to 3 by 2. You divide by 2. Now my claim is once I have Ax equal to B, and I'm putting an underline below the letter if it's a vector, just so that I can distinguish that from a constant or a scalar. So Ax equal to B, I'm claiming x equal to B by A. Does this seem incorrect? No, right? It seems fine. Yeah. I mean, the same idea. We are calling this is also linear algebra. This is also linear algebra. Oh, yeah. Matrix thing is confusing. Yes, it's a big jump from where we were everything was convenient to this. But try to continue along, and at the end of the class, we can discuss more about how to do this matrix thing. So the way you call this, when you write 1 by a matrix, oh, and line under B, I'm just writing this so that I don't confuse with the variable X. X bar is just my vector X. So this thing, this is X bar, this is B bar. That's, or maybe I'm supposed to put it on the top. I forgot. Maybe I'm supposed to put it on the top. Sorry. I think the notation is actually put it on the top. So this is X bar, this is B bar, this is A. So yeah, I think it makes sense to put it on the top. Right, so this is my solution. I'm just writing it so that I don't confuse between the variable X and the vector X. They are two different things, right? So that's why I'm writing a bar or a line on top of the vector. Now, there is a slight mathematicians don't like to keep things very simple. So instead of writing like this, they say, hey, no, you shouldn't write like this. You should write it like this, A inverse times B. Does this make sense? Right, yeah. This is just the same. We are saying instead of writing 1 by a matrix, they just write it A inverse. Yeah, you can imagine it to be 1 by A, but it's not 1 by A, right? Because 1 is a single dimensional thing, right? The number 1, the reason why they came up with this notation is because it's when you had a matrix like this. Let's take a simple matrix. Its inverse is not equal to 1 by this. Because why is it a number? When you had two numbers, its inverse of 2 is 1 by 2, because when you multiply 2 and 1 by 2, you should get 1. That's the end result, right? This is what inverse means. But when you multiply two-dimensional matrix, you are not supposed to get a single number 1. You are supposed to get a matrix like this. Right, exactly. Yeah, so when you multiply A and its inverse, you are supposed to get the identity matrix I, which is just something like this. So this notation, right? So we started off with our equation, we converted it into a vector matrix form, and now we are claiming our solution is simply A inverse times B. Okay, so far with me, is this notation, at least, is this notation clear, or how we came up with this? Is any of this not clear? Okay, cool. So now we simply claim that if a matrix has inverse, I'm going to claim this and say if matrix has inverse, then system of equations have solution. So that's my claim, because if a matrix A has inverse, when I say has inverse, it's not always obvious, right? Like 0 doesn't have a reciprocal. So something like that. Not all matrices have a clearly defined inverse. Same way as 0 doesn't have a reciprocal. If that idea is clear, I'm hoping this idea is clear, right? Okay, so if this is clear, now let's look at how to handle this programmatically. So I'll stop sharing my phone. Okay, stop sharing my phone and okay, I'll start sharing my screen. Okay, and go here. So now let's represent some matrices. I'll zoom in a little bit. Hopefully this is visible to you guys. Okay, so what do we want? We want an array, numpy dot array, and let's take our equation 2 comma, let's say 3 dimensional, so 2 comma 7 comma 51, and then 5 comma 10 comma 4, oops, 4, and then 4 5 32. So I'm calling this A. So let's print A and see. I hope I typed everything right. Okay, so this is our equation, right? This was our matrix A. So why array, why something? Because this library called NumPy does a lot of matrix related operations extraordinarily fast. And that's not extraordinarily fast, but at least in a very numerically efficient way or computationally efficient way. So if we use its arrays, it does it. Now we want to define the vector B. What was B? B is just a vector, but it's also an array. So we'll say numpy dot array, because all, oops. So it's a 3-dimensional thing. We have what is it? 100. Sorry. When I zoom in, it just everything becomes zoomed in. So I print B. So this is my 3-dimensional array. Do I need this? I probably don't need this. If I know this, I get confused with this syntax a little bit, but because I don't use this. No, yes, I was right. Whatever was the starting one. Okay. So now we have this stuff, right? Now our claim is, if I find out the inverse of this B. So just because I don't do this every day, I have a cheat sheet. Somewhere I had opened the cheat sheet for the, oops. No. Okay, so where is in? I think it's just called in. So we go here and then say np dot linealg. So there is a class in that or a module in that called linealg, which has this inverse as a method. So I just invert this and I'll call this A inverse equal to this. So let's print A inverse. So as you can see, it printed some inverse. I'll just zoom in a little less. Can you guys still clearly see my screen? I've zoomed in a little less. Okay, cool. So I took an array, I took the vector and I inverted it. This is just a function that does the inverse. Now I'm going to multiply. So I am saying my solution is equal to A inverse, and I can say again same thing, np dot I think I don't know how to do this. Let's see. Maybe this does it. Let's see. No, this is probably not the one. Let's see, what is this one? No. So I have to do some numpy dot product, and let's do that one. There is a method that does that also. Np dot. Okay, comma b. Okay. A comma b is in our case A inverse comma b. Okay, so it got me the solution. So is this close to our solution? 92 minus 27 and 2. That was our hand done solution, right? Right. So that's it. Now we have figured out how to do this programmatically. So I'll drop all these prints, and solving a system of linear equations is just this much. Now you can say it's a 4-step process because we typed 4 lines in the program, and maybe 5-step process. Right, so that's it. We'll print the solution, got rid of everything. What is the code really doing? The code is doing the same thing that we were discussing earlier on the phone. It's calculating this A inverse really. We'll see how it is doing. If you mean, do you mean what is it doing or how is it doing? Because what is it doing? It's solving. Right, how is it doing? Yes, we'll explore that in a bit. So let's try to do this with pen and paper method now. Why does the inverse dot? Yeah, I'll explain that. Yes. So first, if this, let's go over the pen and paper style, and my battery on phone is reducing, but let me see. If I share, okay. So we were here, right? We had our matrix A, and we had our vector B, and we had our solution. Sorry, we had our vector X and we had our vector B. So my claim was the solution to this system of equations is X equal to A inverse times B, right? This was my solution. So when I say X equal to A inverse times B, to calculate this inverse, I used one function. In NumPy, there is this module called linear algebra, linalg, and that had a function called inverse. Could anyone resend the collab link? I can resend the collab link. Just a second. I think I started in a new collab link, which is bad. Now I have to remember.
My code that is giving me errors.
Yeah, Jonathan, I look at that. We have only 15-20 minutes or so. So I want to first finish what I was starting. So this was this line when I said np dot linalg of A. So I'm doing this. Basically, I'm trying to calculate A inverse by doing this. First, we'll walk through what are we doing. Then we'll see how is it working. Does this make sense? That's the direction we're going. So what are we doing? We're trying to calculate A inverse. So first I represented A as this, right? I represented A as that array. And now I'm calculating its inverse. And I'm storing this in another variable. Is that clear? Okay. Then I'm trying to multiply these two things. If you want to multiply two two matrices, one, because these two are matrices, right? If you want to multiply these matrices, this is one way of multiplying that matrix. So I want to say this. So these are the two lines. They are doing a lot of work actually behind the scenes, but it just looks like two lines for you, for us, because somebody else has written the program to handle all this, right? But it's just two lines for us. So we are saying once we calculate the inverse, I'm going to use that inverse and I'm going to multiply that with vector. So before we do that, let's see what is matrix multiplication as we defined simple ones. So let's take this simple matrix 1, 2, 2, 1. And let's try to multiply this with what is a vector? A vector is a single column matrix. What happens? And the function has no inverse, you'll get an error, some sort of error. Okay, Jonathan's code is giving him error. Let's see what is the error. So Jonathan, the problem you have is array 1 inverse. You have, okay, good one. Let's see. Let me share my screen here. This is a good example of what to avoid. Okay. So Jonathan took two arrays, 1, 2, 3, 1, 2, 3, 1, 2, 3, and another array 2, 4, 6, 2, 4, 6, and 2, 4, 6. Is this matrix, does this give me equations for 3 planes, or is this only giving me one equation? One equation, right? Because Jonathan, that's the problem. Your matrix has one equation, same equation, same equation. When you have the same equation repeated 3 times, there is no inverse for that matrix. It's the same.
So what is the
No.
fix?
What is the what?
What is the fix?
What is the fix? You're supposed to give different equations. Why did you type 1, 2, 3, 1, 2, 3, 1, 2, 3 three times, Jonathan?
It was the simplest of them all, but I didn't expect it to just give me errors.
Right. So it's actually telling you here what is the problem. It's telling you that it's a singular matrix. In fact, if you have watched this movie Interstellar, you guys, or some of you might have watched some other science fiction stuff, they keep using the word singularity. It's a space-time singularity, right? Some of you might have heard it in some movies, some TV shows, wherever. So it's really just this. A space-time singularity is a situation where the matrix corresponding to that situation has no inverse. That's it. It's a space-time singularity. And when you solve some general relativity related equations, you get some solutions that are singular matrices, and those are called as wormholes, and they allow you to teleport between dimensions. All fancy science fiction stuff, but mathematically that's all it represents. So if you change this matrix to something else, maybe like 2, 3, 4 and 4, 5, 6, then
Yeah,
you
I
have a
made
better.
those changes.
Oh, okay, you already made the changes and it worked.
Yeah. Just
Okay.
maybe reload it and those changes should reflect.
That's okay. If you made it, great. I'm not worried about those changes. Okay, so now let's come back to okay, so we were here. What does solution represent again? Solution is the, so you're talking about the variable, right, Shruti? What the solution variable? Yeah, it solves for all three variables. So in our case, when we got the solution, we wanted x, y, and z. Our solution was something like this: 92 point something minus 27 point something, 2 point something. Right? So the solution is x, y, and z. So this is the value of x, this is the value of y, this is the value of z. That solves this system of equations. So before we go into what is happening here, let's look at a simple convention again. So when you are multiplying a matrix, there are a lot of ways of multiplying matrices. So if I do this 2 times this, I don't understand how the equations are being represented as a matrix. Okay. So let's take our set of equations, right? Let me share my screen again. So these were our equations, right? Right, these were our, yeah, my battery is about to die, 15% left. So these were the three equations. What I did is I took the first line, right, the first equation, and I just took the coefficients of each variable. I wrote them as one list or one row of my array. I took the coefficients of the second one, 5, 10, and 4. I wrote them as the second coefficient. And then took the coefficients of the third one and I wrote them as my third list entry, right? Or my third row in the array. So why did I do it this way? Because whether I call this x, y, and z or alpha, beta, gamma, it doesn't matter. My solution is going to be the same, right? So my claim is that only these things influence what is my solution. Only the coefficients are influencing the solution. The name of the variable has nothing to do with the solution. Does that make sense, Arham? Right, because if I call this alpha, beta, gamma, would there be any difference? Wouldn't alpha just be the same answer again? As long as you say 2 chocolates plus 4 biscuits plus 5 cakes cost something, In this problem, if I replace 2 chocolates, 4 biscuits, 5 cakes, why we are converting it? Because people have come up with a, why we are converting into matrix form? Because it's just a convenient way to manipulate the matrices to get solution. So same reason as why, like for example, why do you convert a fraction into a decimal, or why do you convert a decimal into a fraction? Just more easy. What is the math behind being able to convert? There is no math behind this. This is all convention. Converting this to this is all just convention. There is no math. There is math in these two things. I'll explain those. This is just convention. How do the same apply to rules apply to the matrix as the system of equations? Actually, there are no separate things. Matrices were actually invented to solve systems of equations. Right? So there is actually nothing, no separate things. Yeah. So if you want to see matrix, mathematics. So the guy who invented the name Arthur Cayley actually did it for, normally Wikipedia has history sometimes, but this is not there. History of matrices. Matrix theory. So yeah, maybe this one will have it. Yeah, no, it's not reliable, but I also happen to know the history in this case. Okay, so this guy, so they're saying like how initially it started, some ancient Babylonians doing something, then Leibniz writing a letter to L'Hopital saying something about this is solvable because this has a determinant, or this is not solvable because this is a determinant 0. This is all some modern matrix theory, but that he didn't call it determinant, he called it some principal root or something. And then yeah, these guys started doing something, Kramer, and then finally after everybody did this, Gauss did his thing, Lagrange does this thing, finally this guy Cayley, he started writing in this form. In this paper, he used 2 vertical lines on either side of the array to determine their notation, which is now standard. So now this is some maths history from a college in UK. So we should trust them to write their own theories well. Right. So Scotland, not okay. So anyways, so coming back to this. So the entire theory system of matrices was actually initially invented to solve this. And my claim, as I already established, is represent this system of equations in their matrix form, calculate the inverse of the coefficient matrix, and multiply. We will come up with what these things mean. This just np dot simply means multiplying A inverse with B. And we'll see why you have to do np dot also, A inverse with B, and then that gives us the solution. What is inverse? Yes. What is the reciprocal of 2? 1/2. Same way the reciprocal of this matrix is a inverse of the matrix. Exactly. The inverse of the reciprocal of 2 is 2 power minus 1. So same way the reciprocal of A is A power minus 1 or A inverse. Right, that's all. So same style as what you guys, but how do we find the inverse? That's a good question. It's actually a little more complicated to find the inverse. So let me take a simpler example. Now I'll share my screen and I'll say what is necessary to do this. Okay, so now let me share my screen again. Okay, so let's take a simple matrix like this. First thing we want to see is how do you find the inverse, right? So this is my matrix and this is my inverse. I don't know what's there inside of this. My result is if I multiply these two matrices, this might help in algebra homework. Glad if it helps in algebra homework. Hey, don't use these Python programs to solve your homework problems in school. You may not get points. So when you took 2 and multiplied with 2 inverse, what was the result? What is the result of multiplying 2 with 2 inverse? Yeah, your teachers will not give you a full score. So 1, right? So same way, I'm claiming if I multiply my matrix A with its matrix A inverse, I need it to be a 1 and a 1 here and a 0 and 0 here. This is my identity, right? 1 is called as multiplicative identity for natural numbers. This is called as identity for matrices. If you have a diagonal matrix with just ones along the diagonal, right? So what should I multiply here to get this is the question, right? We don't know what to multiply. Without actually deriving this, because I only have 5 minutes, I will tell you what should you multiply. This A inverse is 1 over, take this one and this one, multiply them, and subtract whatever is here and here. So 1 minus 1, 1 minus 4. What did I do? I took the elements that are here and here. I got multiplied them, got this 1. Then took the other diagonal elements, multiplied them, got this 4. And I'm subtracting left diagonal minus right diagonal. Okay. So I get 1 minus 4. Then I take this 1 as is, take this 2, put a negative sign in front of it, take this 2, put a negative sign in front of it, and leave this 1 as is. And I'm claiming this is my inverse, minus 1 over 3, 1 minus 2 minus 2, 1 is my inverse. This is my inverse. So we'll check, is this really the inverse? So to be able, for this to be the inverse, I'm supposed to multiply 1, 2, 2, 1 with this 1 minus 2 minus 2, 1, right? And there is a minus 1 over 3, we'll bring that later. So what happens if I take this 1, and this is how matrix multiplication is supposed to work when you have two matrices. All of this is convention. This is not like a necessary way. There are multiple ways to multiply a matrix, and all matrices have multiple products. This is one product, and this is called the dot product or inner product. And the way this works is you take the first element in the first row, multiply that with the first element in the first column. You take the second element in the first row, multiply with the second element in the first column. So we take 1 times 1, 1, take 2 times minus 2, minus 4. So that gives us the first value in this result. So first element from first row, multiply it with first element from first column. Second element from first row, multiply it with second element in the first column. So rows get multiplied with columns. So you take this, you multiply with this. Could we just the inverse function? Yeah, you should absolutely use the inverse function. There is no need to do it by hand, but I'm just showing it to you by hand so that you know what is happening. Then you take this, you get minus 2 plus 2. Then you take this, you get 2 minus 2. So I'm taking these two, multiplying with these two. So I get 2 times 1, 2, and 1 times minus 2, minus 2. Then I'm taking this and multiplying with this to get minus 4 plus 1. This whole thing is divided by minus 3. So I get minus 3, 0, 0, minus 3. And I'm supposed to multiply all the numbers with minus 1 over 3, which gives me 1, 0, 0, 1. So originally I was expecting to multiply these two things and get this 1, 0, 0, 1. By doing this strange looking technique, I ended up getting the matrix inverse. And when I multiply it, I can prove that it is finally getting me the identity matrix. We'll go on for like 15 more minutes because I want to just finish this thought. And next week, we will again continue with linear algebra. Can you show the technique again? Yeah. So the technique is, let me write the matrix here so that I don't have to keep going back. 1, 2, 2, 1. right? So A inverse is equal to 1 over, this is called determinant of the matrix, determinant of the matrix. And the way you calculate that is you take the principal diagonal, you take the left diagonal, leftward moving diagonal, multiply the elements on the left diagonal. So that gives me a 1. Then multiply the elements on the right diagonal, that gives me a -2, sorry, -4, right? Yeah, exactly. AC minus BD, whatever. No, AD minus BC. So if you want to write this as ABCD, AD minus BC, right? Oops. Right. So you got this, that's the denominator for this 1 minus 4. And then you take the diagonal elements, leave them as is, no changes to them. For the remaining 2 diagonals, flip them and put the, in this example, it's not clear, but let me do, if the matrix was this 1, 2, 3, 1, if I want to invert this, my A inverse would become 1 over 1 minus 6. And then I write the 1, the first one is the same still. Instead of writing this 2 over here, I write this as -2 over here. So what was in rows becomes columns. Yeah, it works for all dimensions of matrices. And that's why this is defined in this crazy manner. When it looks this crazy, the reason is because it has to work for more than 2 dimensions. When you have a 3 here, it becomes a -3 here, and this is a 1. Taking this 1, 2, 3, 1 and converting it into this 1, 2, 3, 1 like this is called transposing. So you're changing all the rows into columns, right? We change the rows into columns. And since we are trying to calculate inverse, we are also putting some negative ones here. In next class, I'll even tell you why or how this came out to be, because this is unintuitive, right? Why did this happen? And you take any matrix, you follow this method, you'll end up getting the right solution, which is why this method is popular. So this is called inverting the matrix. And you could do this method for any dimension matrix, just that it becomes complex to calculate matrix for a inverse for a 3-dimensional matrix. So if I have something like this, just calculating the, so the final answer, no, it's not the transposed matrix alone, right? It's like for a 2-dimensional case, yes, it is just the transposed matrix. For a 3-dimensional case, it becomes little more messy. So let me show you what it becomes. For a 3-dimensional case, you take, so the determinant, first of all, 1 over the determinant, right? The determinant is you multiply along this diagonal. Actually, let me flip my phone and write it, because that way of writing it is easier, because it becomes long. So for a 3-dimensional case, if I had a matrix like this, I will repeat the matrix. I will repeat like a mirror image of the matrix.
Karthik, that's not helping because our screens.
Oh, you
our
can't
screen
see,
becomes
right? Yeah,
vertical.
too bad. Yeah, very bad. Sorry.
It becomes vertical for us. So yeah, keep the
Right,
old
right.
way.
Yeah, yeah. Let's try all the way. Okay. So if I'll try to write small letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 4, 5, 6, 1, 2, 3. And then I take this diagonal, multiply them. 1, 5, 9, 45. And I take this diagonal, multiply them. 48 times 4, 192. I put a negative sign. First one positive sign, second one negative sign, third diagonal again positive sign. So odd multiples are getting positive signs, even multiples are getting negative signs. So 105. So this is -32. Right. So this is the thing that goes in the remainder. That's all. So sorry, denominator. So this is just the -32. So the inverse of this particular matrix. Now we are supposed to solve this one, right? We need to get 9 elements because it's a 3x3 matrix. Its inverse should be a 3x3 matrix. What about 2x6? What about 2 by 6? And 4 by 2. Oh, you're talking about why I'm not multiplying these things? Oh, those, yeah, no, diagonal is anything which has 3, right? Like I want a 3 diagonal. I don't want a 2 diagonal. Yeah, those aren't full diagonals. Diagonals which has 3 values. And then I'm supposed to invert these. The way this works is supposed to take this matrix when I'm trying to calculate what goes into this first cell, supposed to take what is in here and then take this matrix. So 5, 8, 6, 9, calculate its determinant. So 5, 8, 6, 9 is 5 times 9, 45 minus 6 times 8, 48. So minus 3 and multiply with this. So this is minus 3. So each cell involves so many calculations now. Next, when I go to 4, I'm supposed to take, when I'm trying to calculate what goes into the second position in the first row. We'll continue this one next class also, but this is just, so I'm supposed to eliminate this one, take these two, 2, 8, 3, 9, and then calculate its determinant. 2 times 9, 18, 8, 24, minus 6, and multiply with this 4, minus 24. And since it's the even number, add plus, multiply with minus 1. So I get plus 24. And then continue on for each element. So take for each cell, remove that row, that column, whatever is the remainder, calculate the determinant of that remainder, and then multiply with whatever is the value in that position, and either multiply a +1 or -1 if it's an even place or an odd place. So we continue this method to calculate the inverse. Now, does this look simple? Looks simple. Does this look tedious? Right. If for someone it is not tedious, I would like for them to tell me what are the remaining elements. If it is not tedious for someone. Yeah, because it's a boring exercise, but I'll give you one homework problem just so that you guys can continue and complete this. So how to calculate inverse? For a 2-dimensional matrix, inverse is simply if it is A, B, C, D. For a 2-dimensional matrix, determinant is defined like this. It's AD minus BC. So one diagonal with another diagonal. And then you take A, put minus B here, minus C here, D here. This is a inverse for 2-dimensional matrix. For a 3-dimensional matrix, it just looks very complex. So I'll say this is A11 and this is A21 and A31. A in the third row, first column, A in the first row, first column. What is the point of the determinant? So determinant represents like roughly the size of a matrix. Okay. So what does that mean? Like if you have a matrix whose, so if I drew a matrix has 4 coordinates, right? A, B, C, D, or it has 4 points. A 2-dimensional matrix has 4 points. If I drew a parallelogram with vectors on this, with sides, or with these 4 points, A comma B is one of the points, and C comma D is one of the points. If I drew a parallelogram like this, so this area is the determinant of the matrix. So it has a meaning. What is the point when you're trying to invert a matrix? How do you graph a matrix to find the area? You don't graph a matrix. No, this is not the graph of a matrix. This is the area of a parallelogram where 2 of its points are the coordinates in this matrix. So I have one A comma B, one C comma D. If I drew a parallelogram with these as the vertices of a parallelogram, then the area of that parallelogram in 5 more minutes will be done. Yeah, is the determinant. It's roughly represent what's the size of a matrix. So if I take a matrix like this, you should not think of it as the number size 10, 20, 30, 40. the size of this matrix is roughly 200 minus 1200. It's minus 1000. So it's a way to assign some size to that matrix, because when you are trying to invert a big thing, you want to divide by a big number, right? So when the inverse of 200 is 1 over 200, inverse of 2 is 1 over 2, right? You want to divide some sort of a scale to this. Whereas the inverse of 200, 300, 400, 900 versus 2349. These two inverses should not look the same, right? Like they should have a different scaling. So this represents roughly like what's the size of the matrix, or what's the extent to which the matrix has grown in size, right? If you draw a parallelogram with 200, 300 and 400, 900 as the vertices versus with 2, 3 and 4, 9, one parallelogram looks tiny, other parallelogram looks gigantic, but they are really both, we claim that they are in the same size. You can shrink one to become the other, is the claim. Of course, I don't know if this is true here, but that's the claim. So that's why there is a determinant for a matrix. Does that make sense? Yeah, they're similar parallelograms. Yes, they're similar parallelograms, and we want their inverses to reflect that way. So it should have like minus 1 over whatever big number here, its determinant, and minus or 1 over its determinant here. So it represents, it's scaling down everything. Yeah, this is pretty confusing. We'll continue in next class, but I would like for you to just go through it numerically. Is this part clear? At least is this part clear? How to go through this numerically, right? So I would, one of the homework exercises, take this matrix and try to calculate its inverse by hand. The other one is take this program, whatever we had as a program here. My battery is almost about to dry. I'll give you this program and a different problem, not the same problem. Try to represent a system of, try to write a system of linear equations, represent them as a matrix, and try to calculate its inverse and multiply its inverse with this B to calculate the solution. So that's another set of problems. So those are the two. When will we get, yeah, actually I didn't have time at all to write the solutions. We'll write solutions and then, yeah, I'll share this collab link with you guys. So this is a way to solve linear equations using Python and using numerically. We can see how to do this graphically, but I'm afraid it will be like very messy. It may not look very clean. I'll have to see if there is a nice video somebody made of how it looks, because I myself don't have the creativity to do this graphically and make it look nice. Let me see if I find a nice visualization. So just to summarize what we learned in this class, and then we can just drop off. We saw how to set up when there are a system of two equations in two variables, you can substitute one variable or express one variable in the form of other, substitute that in the second equation and solve it. Or you can eliminate one variable from the pair of equations and then you'll just get one equation with one variable and solve it and then substitute the answer back. So you either substitute and solve or you eliminate and solve. Those are the two methods. You can, how many number of solutions does an equation have is determined by how the coefficients behave. The same thing is doable in 3 dimensions when you have 3 equations in 3 variables or more, but it's very tedious. One way to solve, reduce the amount of tediousness is by, or one way to guarantee how, so it's no less tedious if you go to matrices. To find out when a matrix is solvable or not, when a system of equations is solvable or not, when it was in 2 variables, it was this easy thing. We could say a by d equal to b by e or whatever, and then you know whether it is solvable. When it is in 3 dimensions or when 3 variables, 3 equations, it's very difficult. Hence, people invented this matrix theory to understand when it is solvable or not. And that the motivation is simply elimination. You use elimination, you can still solve using matrices and Gaussian elimination, or we can solve using this matrix inverse. Those are two methods. And that's, we can stop here. Sorry for going over 14 minutes. If you don't have any other questions, you guys can drop off. If you have some questions, you can stay. Thank you.
Bye. Thank you.
Bye. Thank you.
Bye. If any of you have
Don't forget to subscribe and like. If you have any questions, you can email info@agoramastercode.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!